ultrasound artifacts? Artifacts are simply something that appears on the ultrasound screen that does not reflect reality. It's artifactual. See, ultrasound technology makes certain assumptions about the speed and the direction of sound in tissue. If these assumptions are violated in any way, it results in artifacts. So here are the assumptions that the ultrasound machine makes. It assumes that the waves travel in a straight line from the transducer to the patient. It assumes then that the reflections back from the patient also travel in a straight line back to the transducer. It assumes that this travels at 1540 meters per second, or average speed of sound in soft tissue. It assumes that the amplitude or the strength of the returning echo is directly related to our patient's tissue characteristics and not something else. It assumes that the scanning plane is very thin, and it assumes that reflections that come back are only arising from the beam's main axis. So let's look at some examples of ultrasound artifacts. It's important both to understand why the artifacts occur and also be able to have the pattern recognition of what they look like. So the first one we're going to discuss is shadowing. In shadowing, the concept is pretty simple. You have the ultrasound transducer that sends out an ultrasound wave. It hits a structure that is highly reflective, dense, and unable to transmit a sound wave through it. Therefore, it reflects all of the sound waves back to the transducer. Now, to the machine, because no ultrasound waves are transmitted through, then to the machine there's nothing beyond there. And so it appears as an anechoic area beyond that highly dense reflective structure. And this is called shadowing, as if there is a curtain or a shadow beyond the reflective structure. Now, sometimes this is very clinically useful, as in this case, these structures here are gallstones. And the fact that there is posterior shadowing helps us know that they are gallstones, but the shadowing is an artifact, because in fact there is structures visible beyond that area. They're just not visible to the ultrasound machine because the sound waves cannot penetrate or see through the gallstones. Next, let's discuss edge artifact. And while edge artifact may be a little bit more difficult to understand, it's very easy to recognize. You have the edge of a fluid-filled structure here, and you have what appears to be shadowing beyond it. Now, this is different from the shadowing that we previously looked at. It appears to arise from the edge of that structure. Edge artifact arises from two main things. One is refraction, and if you remember from the physics lecture, if you have an ultrasound beam that's coming at an oblique incidence from a fluid-filled structure, because of the change of speed of sound through the soft tissue to the fluid-filled structure, that sound wave bends from its original trajectory. Then when it comes back to the ultrasound transducer, it assumes it arrived from here instead of from here. Because remember, the ultrasound machine assumes that the sound has traveled in a straight line. But in this case, it's bended. It's refracted. So that makes it appear that there's no echoes arising from this area, and hence the machine displays it as black. Furthermore, you have scatter. Now, scatter arises because the ultrasound wave hits the edge of this structure and scatters the beams. And because those beams never make it back or return back to the ultrasound transducer, furthermore, the ultrasound machine thinks no echoes are arising from this area, and that's why, again, it looks anechoic or black. Now, it's important to recognize edge artifact because this is not true shadowing in the sense that we previously discussed. And in the case of the gallbladder, shadowing may help you diagnose gallstones, where edge artifact could be mistaken as gallstones if you don't recognize the artifact properly. One way to tell the difference between these two is if you change the direction of incination, meaning the direction that you're shining your ultrasound beam. So just fan it, image from a slightly different angle. True shadowing that we previously discussed will stay there because there's a real gallstone there that's causing the reflection. If it's edge artifact, it will change directions and start to disappear because you're changing the angle of incination. The next artifact I want to discuss is reverberation. And reverberation is very familiar to us. We've all sung in the bathroom shower, and our voice is going out and reflecting off of the tile, the walls, the ceiling, and the summation of all of those reflections arrive back at our ear, and our brain interprets that as that reverb type of sound. It's because it's actually a summation of lots of different reflections. The same principle applies when you're in a canyon and you're yelling, and you hear that echo come back. The only difference is because there's more time that it takes for that reflection to come back, your brain can distinguish that as a separate sound, and it's heard as an echo instead of just a reverberated sound. Both principles apply in ultrasound as well. So in this example, here's the pleural line. It's a real structure, it's not artifactual, in the lung. And you have your ultrasound probe here, and it's going to send out a sound wave. That sound wave hits the pleural line, is reflected back. So that's reflection number 1. And we'll say that took time number 1 to return. And so the ultrasound machine displays that as the pleural line. But this same ultrasound wave, or the same echo, then continues reflecting off of the ultrasound transducer back to the pleural line, back to the ultrasound transducer. And then this is reflection 2, and it took time 2 to return. And time 2 is double the time of the original time. So the machine says, oh, that means there is a pleural line equidistant below that original pleural line, because it took twice the amount of time. But in fact, this is not a real pleural line. It's artifactual, and it occurs because of the reflection of the original sound wave. Now this process continues. This sound wave, the second reflection, is reflected back off of the transducer again, back to the pleural line, back to the transducer. And that's the third reflection, and it takes 3 times the amount of time. And so the ultrasound machine says, oh, well, it's a line 3 times the depth of the original line. And then this process continues and continues, producing these equidistant reverberated lines that appear to look like the pleural line. So reverberation has this principle of equidistance because of the equal reflections, and it also has the principle of attenuation. You'll notice that with each reflection, the pleural line appearance is less bright. That's because this first reflection has the highest intensity of the returning echo. The next one has a little less intensity because of attenuation, and the next one has a little less attenuation. So it appears as bright, less bright, less bright, less bright, and eventually it goes away. Or reverberation would inherently appear indefinitely. So that's reverberation, and it has to do with the reflection of the sound wave between 2 reflective surfaces, producing this equidistant, reflective type of appearance. So the way you're going to identify it is it's going to appear as equidistant lines attenuating from a highly reflective surface. All right, well, that was a discussion of the artifacts of shadowing, edge artifact, and reverberation. In the next video, we will cover the artifacts of posterior enhancement, mirror image artifact, and compression.